In the previous lessons, we looked at vectors geometrically, okay? As you can see here, we've got four geometric vectors. They're the directed line segments. Today, what we're going to do is we're going to see how they relate with algebraic vectors. What are algebraic vectors? So we have some definitions that we have to go through, some understanding, and then what we're going to do is we're going to take a look at all the operations that we've done before and see how easy it is to deal with all the operations with algebraic vectors as opposed to drawing out all the geometric vectors. Okay, but how we're going to start with is if we take a look at these four vectors here, all right, what we want to notice in there, okay, we put these vectors on a grid. Okay, now what we can notice, if we take a look at any one of these, we can see that from the tail to the head, we travel 4 units to the right and 3 units up. Take a look at B, vector B is the same thing, 4 units right, 3 up. Vector C, again, 4 units to the right, 3 up. And finally, vector D, 4 units to the right and 3 up. Okay. Now, the reason why we did this is to show that these are all equal vectors. Okay. So vector A is equal to vector B. They're equal to vector C, equal to vector D. Why are they equal? Because they have the exact same length and they're in the exact same definition or direction. Okay. So to convert these, because we have a direction when we say we're going to go 4 to the right and 3 up, since we're on a grid, we know that we have these coordinate points, right? And coordinate points, if we look here at, let's say, the head of C, vector C as P, we know that the coordinates there are 4 and 3. Well, in vector world, when we travel, we say we give components, okay, to the vector. We use square brackets to denote our direction, and basically it can give us the magnitude as well. But we say, okay, well, we travel 4 to the right, that's the first x component, and then we travel 3 up, that would be the y component, okay? So one of the things, or a couple of things that we have to realize that we have here is that this is a vector, all right? It has square brackets, all right? This is part of communication. We have to make sure that the vectors are in square brackets. Now, textbook doesn't give you square brackets, it gives you rounded brackets. It's another problem with the textbook, but I want to make sure that when you give me vectors, you're giving me square brackets, okay? If you give me round brackets, then you're giving me a point and not a vector, okay? The other thing is that we've learned in this one is that the 4 and the 3 are the components of a vector, okay? Whereas round brackets for the point, you've got coordinates. For a vector, you have components, okay? So make sure that you've got that as well, all right? We can see that all 4 of these are equal to each other because they have the same direction, same magnitude as we said before, okay? And so the other thing is we can say that if 2 vectors have the same components, then they are equal. Okay? Again, if you can go from one to the other, all right, by the exact same method, we're traveling 4 to the right and 3 up. 4 to the right, 3 up, exactly the same method. Then you can represent each of these vectors, okay, one way. All 4 of these vectors are represented with the brackets, square brackets, 4, 3. Okay, the components 4, 3. They are equal to each other. So in essence, what we're doing is we can say that vector A, vector B, vector D can all be translated to vector C. Okay, they can all be represented with vector C. All right. Vector C is special because it has its tail at the origin. Okay. All right. And if a vector has its tail at the origin, all right, what we say is we have a position vector. All right. Any vector that has its tail at the origin at 0, 0 is the position vector for all other vectors that are equal to it. Okay. So if a vector has its tail at the origin, then it is considered to be a position vector. Okay? The position vector has the tail at the origin, and if you notice our vector C up here, its head happens to be at the point 4, 3. All right? In general, okay, I'm going to put there and down. In general, for any position vector, whose head is at the point xy, the vector can be represented by square brackets xy. Okay? So if we were to use the vector, okay, or the grid up here, all right, and we were just to make another vector, let's say we've got the head up here, and that's the point xy. We know that this is, what, 1, 5, whatever. But the position vector in black that I'm drawing out here is represented by square brackets xy. Okay? So that's what we have for the position vector. All right? We have square brackets for a vector. The components make up the vector itself. It tells us where we're going. A position vector, goes from the origin to the head, all right, of the vector itself. Okay. Now, what we're going to take a look at is some operations on vectors. Okay, on these algebraic vectors. All right. So how we're going to do this is we're going to take a look at a couple of examples geometrically and see how quickly we can do these algebraically. Okay, so we're going to say we're just going to be given, we'll say two vectors here. We'll use the position vectors. We'll say -1, 2, and we'll use the vector v, and let's say that that's 3 and 5. Okay, so 3, 5. So we've got two vectors. We want to determine what u plus v is equal to. All right, so that's the first one. We'll look again at subtraction, and we'll have a go at scalar multiplication here. We'll just say that we've got 2 times v, let's say. Okay, so again, I'll just see if I can set up a grid here. Okay, and all right, so we've got our grid. Let's take a look at the first point. We've got u plus v. Well, u is -1, 2. So -1, 2 is this vector right there. We know that that's u. 3, 5. So we have to start at the head of vector u. We go to the right 3. 1, 2, 3 and up 5. 1, 2, 4, 5. And it looks like we're at the point 2, 3. So if I were to just kind of draw that out, well, that turned pink, weird. But let's say it's that one right there. This is the u plus vector v. We see we start at the origin and we end up at 2, 5, or sorry, 2, 3. So that means u plus v is the vector 2, 3. Oh, wait, did I do that right? Oh, you know what? I can see what I did wrong. It's not 2, 3 because I did u incorrectly. You guys probably caught that on me. That's okay. Let's see if we can make this a little bit better. So u and v, or sorry, u is -1, 2, which should be up here. Okay, that was my fault before. V, 3, 5. So again, we travel over 3. So 1, 2, 3, up 5. 1, 2, 3, 4, 5. It's up there. Okay, there's our V. And now I can take a look at drawing U plus V from the origin up to what we have is 2 and 7. So the head is 2, 7. So U plus V is 2, 7. All right, so we'll make that change, and now we can take a look and see, all right, what we've got with the coordinate or the components, right? How do you combine the x components in order to get the final x component? Hopefully you see that all you do is just add the two x components together. -1 plus 3 is 2. When you take a look at the y components, what do you do with the 2 and the 5 to get 7? Again, add. So adding just means you add the components together. Okay, you add the components. So I'm going to put that down in there. Add the components. Okay, these are the corresponding components. You add the two x's together, you add the two y's together. All right, now let's take a look at subtraction. We hope that that's the same thing, where all we have to do is subtract the components together. All right, well, let's see, what would it be if we were to do that? -1 take away 3. All right, -1 take away 3, -4. 2 take away 5, -3. Let's see if that works out for subtraction. Okay, I can quickly take out the u here, or the v rather, get rid of the adding part. So remember with subtraction, what we have to do is we add, or we line up the tails, all right, together. So what is v? It is 3, 5. So from the origin, we 1, 2, 3, 1, 2, 3, 4, 5. Okay, that's v. And how we subtract, we go from the head of the second to the head of the first. So from V down to U. And what did we do? How did we get there? If we take a look, we go 1, 2, 3, 4 to the left. Well, that's a -4. And we go 1, 2, 3 down. That's a -3. So you can see that this is, in fact, -4, -3. Okay, so it works the same way. We subtract the components. Okay, that's what we have there. So it works out. The adding and subtracting is so easy. You just basically add and subtract the components and you're all set. So what do we do with the multiplication? Do we just multiply the components together? If we were to look at this and say, well, what's 2 times vector v? Do we just say that this would then be 6, 10? because we just multiply the 2 by 3 and the 2 by 5? Well, if you take a look over at our example, and if I can kind of get rid of everything we don't need here, well, we do need that, so I'll add that back in, all the way up. It's not straight, I get it, but what we want to do is we want to get to the our final answer. 2 times vector v, well, again, I'd have to come over from the head of this v and come over 3 again. So 1, 2, 3, and then up 5. 1, 2, 3, 4, 5. We're way up here. So 2 vector v, notice that we are literally at the head of 6, 10 right there. So 2v is in fact 6, 10, the vector 6, 10. All right. So we have to understand, what our operations are. Okay. So in summary, vector addition. Okay. So for vector addition, we add corresponding components. For vector subtraction, we subtract corresponding components. And for the scalar multiplication of a vector, we multiply the scalar by the components. Okay, so that's what we've got there. All right. Now, one of the things that we can do with this or try to figure out is we're going to try to see if the distributive property holds true over this vector addition. Okay, the addition of the scalars themselves. All right. So what we're going to do is this. I'm going to say the distributive property. Distributive. It's in there somewhere. Trust me, all the letters are there. The distributive property. All right. We're going to prove that if we have 2 scalars added together times a vector, then that's going to be the one scalar times the vector plus the other scalar times the same vector. Okay, and we're just going to give the conditions here where m and n are scalars, real numbers, and the vector u could be any position vector or any vector xy. All right, so here's how we prove it. All right, we'll put the proof down, take a look at it, and we start off with the left side, okay, for the proof. Well, what this is if we take a look at rewriting this just slightly so that we have in vector notation here, times the x and the y. We know that the x and the y's are scalars, so we're just going to do some scalar multiplication here. M plus n, right, is a scalar times the vector. We just figured that out, so we know that that is the vector m plus n times x, and it's m plus n times y. That's scalar multiplication. If we look at each component inside, these are scalars. So we know that scalar, the distributive property of scalars work. So we can say that's mx plus nx, my plus ny. All right. And then what we can see here is that is vector addition, right? So we can take the vector addition and go the opposite way. So we have mx, my as one vector. We add that with nx, ny as the other vector, and we can see that that is m times vector u plus n times vector u. Okay, so there's our proof. So we proved that there. Okay, one more things that we have. All right, now let's take a look at a couple of other things, okay, as we go through this. And if there's anything, if we're going, too fast, whatever, you have the opportunity. You can always stop this, rewind it, and go through it again. All right, so let's take a look at what we can do with some of these vectors here. So let's take, we'll say example 2 here. We want to look at a vector. Let's just say we've got a vector AB. Okay. Vector AB has the endpoints. So what we're trying to do is find out what is the position vector. Okay. So vector AB has endpoints. Let's say A is the vector, the endpoints -2, 6, and B is 4, 3. Okay. What we're going to do is we're going to determine the vector itself, the components, okay, or find the position vector, determine the position vector for AB. And here's a new concept for us. We're actually going to determine the length, we're going to find the magnitude of AB itself, okay, algebraically. All right. So here's what we can do for the first part, finding the position vector. And this is when we do it with this example, we can do it for all. All right. If we look at the points and we'll just very quickly draw in our coordinate here, and we say -2, 6. So -2, 1, 2, 3, 4, 5, 6. It's up here. There's our A. 4, 3, 1, 2, 3, 4, 1, 2, 3. There's our B in this one. Okay. Well, what we see here is we actually, from A to B, we have to drop down 2, right? So we know already that our X component is -2. All right. Now to get all over to B from here across, we go 1, 2, 3, 4, 5, 6 to the right. So there's our 6 right there. Okay. Did I do that right? Oh no, I only went up. No, that's 6, down 3, down 2. You know what? I'm going backwards on this one. Look at that. You guys must think I'm nuts in here. It's just because I did the -2 first. All right. Let's see. Did I get it? 1, 2, 3, 4, 5, 6 is up there. This is -3. There's the A right there. That's -3. That's obviously in the Y direction. So the Y component is -3. The X component is actually 6 to the right. So there's our 6 that way. Okay, now we're actually understanding what we're doing. You guys are looking at this going, he's nuts. Anyhow, so now we have where our vector is. Now we want to be able to do this algebraically, right? So that we don't have to always put our points on the grid and then, go from one point to the other and figure out our components, right? So if you take a look at the points themselves, all right, and convert them, and here's what I mean by converting them. We're going to convert them to position vectors. We want to get to a vector. So if we take a look at, see, here's our origin there. If we look at the position vector OA, see, OA is the vector negative 2, 6. OB is the position vector for 3. All right. If you look at the diagram OB, OA, and then AB, you can see that that sets up a subtraction of vectors, right? That's a subtraction of vectors right there. OA and OB are lined up tail to tail, right? We're traveling from the head of the second to the head of the first. The second is OA. So we can say here that our position vector is OB minus OA, from the head of the second to the head of the first. See that? If we look at this as components, so this is what you need to see and need to know algebraically. If you look at it and sort of we can prove ourselves here and say, well, OB, right, is 4, 3 minus OA, which is negative 2, 6. Okay. 4 take away positive 2 is 6. 3 take away 6 is negative 3. Okay, so you can see that how that works out. All right, so understand that when you take a look at, if you just have the endpoints, you can quickly go to what the position vector is. Okay. The other thing that we looked at, or what we can look at here, is what is the magnitude? So we're looking at the magnitude of the position vector itself. So how can we take a look at this vector 6, negative 3 and find out what the magnitude is? Well, if we really get rid of these other two position vectors, we already have our clue at how to figure out what the magnitude should be, how we do this, right? We have a right angle triangle. We know we have 3 units on one leg. We have 4 or 6 units on the other leg. We use the Pythagorean theorem, right? We use the Pythagorean theorem on this, okay? So if we want to figure out, just the straightforward magnitude, the Pythagorean theorem, we use the square root of our x squared. So 6 squared plus y squared, right? And then we can work out, there's 36, 9, square root of 45. Okay? So the magnitude itself. If you have a position vector, all right? So we can say, therefore, for all vectors xy, the magnitude of xy is equal to the square root of x squared plus y squared, just by using the Pythagorean theorem. Okay? All right. A couple more things to do. I know it's a lot in here. All right, again, you can always stop and go back and, pause or whatnot. I've got 2 more things. First of all, I'll do the quickest thing to start off with, and then I'll do the last part here. So this one's called, we're going to say I'm going to put it in underline, the unit vectors. The unit vectors. Let's take a look at what the unit vectors are. They are specific. The unit vectors, okay? There's 2 of them. One's called I and the other's called J. They are specific. If ever you see an I, a vector I, it is the vector 1, 0. The J is the vector 0, 1, okay? They are the unit vectors because they have a magnitude of 1. A unit, right? A magnitude of 1. all right? And they are along the major axes, okay? The X and Y axes, right? And that's what the unit vectors are. So with our, with any vector, we can say, let's say we'll do an example of why we use these. Sometimes they're expressed, vectors are expressed as a unit vector. We can say 6, -3 is the unit vector, or in unit vectors would be 6i. Sorry, it looks more like a J in here. I'll clean that up. 6i minus 3j. Okay, that's how we use the unit vectors when you look at them. Okay, so we can quickly see this. Well, if I is 1, 0 and 3, or sorry, and j is 0, 1, if we do the operations on this, we have 6, 0 minus, we can say 0, 3. So add these or subtract these together, you have 6, -3. Okay, so that's set there. Basically what we've done is we've taken these two vectors. We know that they are non-collinear, all right? And we've expressed any third vector as a linear combination of those two. Now, we did that yesterday, okay? When we talked about linear combinations. Any two non-collinear vectors can basically be expressed as a linear combination for this third vector, okay, or any third vector that's on the plane, all right? I and j are special because they are the unit vectors, all right? But this works for any vector themselves. If we just take a look at linear combination, we can find it. Linear combination of vectors, and this is the final thing we're going to do. We could just pick any old random vector, okay? And so what we're going to do is we'll just pick, let's say that we have the vector 2, 3. We have another vector, and it's, let's say 1, 4. Okay, we're given these two vectors. Let's express a third vector. We'll call it 4, -4. All right, as a linear combination of v and u. Okay, well, here's how we do it. Okay, here's a solution. We take a look at v and u, and we notice that they are non-scalars of each other, so they're non-collinear. Okay, so we can come up with a linear combination. So what we do is we set it up as a linear combination. We assume that there is one. So we can say, okay, well, W then is a linear combination of V and U. And so S and T are just some scalars. We don't know what they are. We just have to figure it out. So we substitute the W with the components that we know. All right. And do the same for the V and the U. Well, if the left side is equal to the right side, okay, because they have to be equal vectors, the components must be the same. We then come up with two equations, one for the x component, so that would be 2s plus t, and one for the y component. -4 equals 3s plus 4t. All right. This is how we figure out or solve for s and t. From here, what I want you to do is I want you to solve this linear system. Right? You can use substitution or elimination. All right. And from that, okay, you will then find out what the S and T's are. All right. So when you do this, you should come up with the S and T's basically working out so that you have 4V minus 4U. Okay? And that's the process. All right? So that's everything there. I know it was a very long one there, but there was a lot of information to go through. All right? We could take a look at basically this homework here to help us understand what the algebraic vectors are. And if you're like me, you'll soon find out that algebraic vectors are a lot easier to work with than the geometric vectors. Okay. One last thing that I noticed when we were on here is you can convert any vector into its own unit vector. Okay. What that means is if we've got a vector this long, if it's not a unit vector, let's say the unit turns out to be only this long there. So this is of length 1, all right? The unit vector for a different vector, right? Let's say the full vector here is, we'll just go back to vector u, all right? Well, basically the small vector, the unit vector, is the vector u divided by the magnitude of vector u. All right. So if it's of length 10 and you divide by 10, you get down to 1 again. All right. So there's the unit itself. You get a magnitude of 1 in the same direction as u is here. Okay. That's what this is up there. All right. Good luck with the work.